Hello guys, this is 7.1. We are going to look at our first integral for the class, 7.1, where we're going to look at logarithm defined as an integral. So in this section, we'll introduce the natural log function using definite integrals. However, to justify using the logarithm terminology, we must show that the function we introduce satisfies the usual properties of logs. We will do so using our definition and the calculus property which it satisfies. So first, let's look at the definition. For any positive x, we define the natural log function as ln x is equal to the integral, definite integral 1 to x of 1 over t dt. Now, keep in mind that this is the definition. It follows that for x greater than or equal to 1, ln x is the area under the curve of y equal to 1 over t. Let me give you a quick sketch. All right, so suppose we have a curve like this, the red curve, that's y equals to 1 over t. All right, so what we're saying is the area under the curve, it's between 1 and x. So this area is equal to ln x. Okay, so that's basically what the definition is saying. All right, and to put it in another sense that we understand it a little more is to we'll look at some example in a second. But let's just do a quick review on the number e. All right, so the number e satisfies ln of e is equal to 1, right? And numerically, we know that e is approximately 2.71828, and so on. And this is a very interesting number, this e, right? Because it's like pi, it's a transcendental number. It means, it goes on forever and never repeats itself. In this number, we're going to look at how we can derive this number using sequences and series later on in the semester. All right, but I think that's enough background for now, and let's look at our first theorem. Theorem 1, for any positive x, we have the following. The derivative with respect to x of ln x is equal to 1 over x. Okay, which we're pretty familiar with. In Calc 1, we learn a lot of different differential rules, and this is probably one of them. When you take the derivative of a natural log, you just push down whatever it's within the log into the denominator. All right, and of course the chain rule applies as well. Let's say we're taking i.e., let's say we're taking the derivative of some ln of u of x, right, like that. So same thing, you will push down whatever is within the log u of x, the whole function u of x, into the denominator, and then apply the chain rule, means you have to multiply by u prime of x, right? And whatever u is, you take the derivative of that, and then if extra rules is needed, then you apply that as well. Okay. Now let's do a quick review on some of the properties for both logs and exponential. All right, so feel free to pause the video here if you want to take a look at some exponents for e to the x. Right, so we have the product rule, we have the quotient rule, we have the negative exponent rule, and also the power rule. Right, so we're pretty familiar with this. All right, and next we have kind of like the definition to convert between exponent with natural log and just a regular exponent with base a. Right, so we have a to the x power is equivalent to e to the power of x times ln of a. All right, and here are some rules for log with base a. And again, we have the product rule, the quotient rule, the reciprocal rule, and the power rule. And again, feel free to pause the video if you want to take a look at these. All right, so the main idea we're going to use for indefinite integral, if we have 1 over x, integral of 1 over x dx, this is ln x plus c. Now, of course, here we're assuming that x is positive. Now, if x is not positive, then usually here we will add an absolute value here to denote that we want to make sure that x is positive. All right, so let's jump into our first example. All right, our first example, we want to evaluate this definite integral from negative pi over 2 to pi over 2 of 4 cosine theta over 3 plus 2 sine theta. Now, this looks crazy, right? So a few techniques that we learned from Calc 1. Of course, the most popular one is substitution. All right, so let's see. We have 3 plus 2 sine theta in the denominator. Right, now we have 4 cosine theta in the numerator. Now the derivative of sine is cosine, right? So we see some sort of chain rule happening here. All right, so let's try doing u sub, right? So I'm gonna let u be 3 plus 2 sine theta, right? Then du is going to be 2 cosine theta d theta. All right, so we have the 2 cosine theta d theta right here, right? So that gives us some idea of what we can replace. Now, of course, there's an extra 2 in here, so we have to bring that out. And then the denominator, we have 3 plus 2 sine, which is just our u. All right, so let's go ahead and apply u sub, and let's see what we have. Is equal to. I'm not going to worry about the bounds yet. We'll take care of that after we finish this part. All right, so the numerator, 4 cosine theta, but du is 2 cosine theta. So we have 2 times du, right? That includes d theta as well. So this whole thing in the red circle, that is 2 du. All right, all over 3 plus 2 sine theta, that is just u. Okay, we have the du right here. We have the u. All right, now let's take care of the bounds. So we have to plug in negative pi over 2 and pi over 2 in here. All right. So let's say new bounds. Right. So lower bound is going to be 3 plus 2 sine theta, sine of the lower bound, which is negative pi over 2. Sine of negative pi over 2 is negative 1, so we have 3 minus 2, which is 1. All right, and upper is going to be 3 plus 2 sine pi over 2. And it's going to be 3 plus 2, which is 5. All right, so our new bounds are 1 to 5. Okay, now let's look at this definite integral right here. If we clean this up a little bit, I'm going to rewrite that as 2 times the integral from 1 to 5, 1 over u du. Right? And we know that the integral of 1 over u is just ln u. right? So that is 2 times ln u, and then evaluate it from 1 to 5, which gives us 2 parentheses ln 5 minus ln 1, right? And what is ln 1? That's right, it's 0, right? So this simplifies to 2 times ln 5. All right, and let's do e to the x next. So we know that the derivative of e to the x is itself, right? Therefore, the integral of e to the x dx is itself. But remember that that is an indefinite integral, right? So don't forget to include our friend here, plus c. Okay, so here's something you can do to remind yourself that you always want to add c after an indefinite integral. So take like a sticky note or a piece of paper and write plus c really big on the paper and tape it next to your computer screen, right? And whenever you see that, you can go back and check, okay, do I need to add c to this integral or not? Right? That's one trick I used to do in class. I would write c on the top right hand side of the board, and then that reminds us to add c if we're working with an indefinite integral. But since we're working on a computer, you can have c somewhere else, maybe as your background on your laptop. That would be pretty cool, right? Now, what if we're working with an exponential expression that does not have e as the base? Let's say we have a to the u, where a is some number, and u is a continuous function of x, right? Then if we want to take the derivative of a to the power of u of x, right, then the derivative is equal to a to the power of ux times ln of a times du dx. Right? Even though we don't run into these type of derivative very often, but it's still good to have it in the back of your mind. Now let's take a look at what happens when we want to integrate this. And it's pretty simple, actually. So the integral of a to the u is itself a to the u over ln of a plus c. And we know that since a is just some number, ln of a, that's just a constant, right? So it's actually pretty easy to work with. And if you think about this, if a, the number a is e, Euler's number, then in the denominator, ln of e, that's just a 1. That means we have just e to the power of u here, right? So it all makes sense, right? A is just some other number. All right, and that's I'll do another example, right? Let's say we want to take the derivative of this standard log base 10 of 3x plus 1. All right, so let's see. First, we don't know how to work with normal log, right? We only know how to work with natural log. So first thing we're going to do is we are going to do a change of base, right? Hopefully you guys remember how to do change of base, right? So let's say if I have log base 10 of something, then I can rewrite this as a quotient of natural logs, right? I can write this as ln of 3x plus 1 over ln of 10. Okay. Now, if you need a quick review on change of base, I'm just going to write it on top of here, right? Log base a of b can be equal to log natural log of b over natural log of a. Right? This is essentially what we're doing here, because we have no idea how to work with log base 10, but we know how to work with natural log. And the nice thing here is, if you look at the denominator, log base 10, log ln of 10, that is just some constant, right? So we don't have to worry too much about it, and we can just bring it out of the derivative, leaving on the outside, right? And then multiply by derivative of ln of 3x plus 1, right? And this is pretty easy to do, right? 1 over ln of 10 multiplied by, so push 3x plus 1 down to the denominator, right? 3x plus 1. And don't forget to multiply by the chain rule of 3x plus 1, that is a 3. All right, so let's clean this up a little bit. We have 3 over 3x plus 1 times ln of 10. Okay. And that's it. Okay, so next let's do an integral. All right, so for part B, we want to integrate log base 2 of x over x. Now, when you see log of some base that is not e, or when you see log that is not natural log, always apply change of base first, because that might clear things up a little bit, and then you have a better idea on how to approach these type of integral. Okay, so let's go and do that. Right, change of base, log 2x, so that gives me ln x over ln 2. Right? So this whole thing, right, this whole thing, ln x over ln 2, replaces our log base 2 of x. Okay, and then we need to multiply by another 1 over x, right, because of this x right here, right, dx. All right, so let's see what we have. Let's clean this up a little bit, bring out the ln of 2 in the denominator. So we have 1 over ln 2 multiplied by the integral of ln x over x dx. Okay, so this is a pretty interesting integral here. All right, we have ln x on top and x in the denominator. Now, I believe now you guys have tools to integrate this. So if you want, you can pause the video and try to evaluate this integral on your own. So the idea here is we're again going to do u sub, because we see the relationship between ln x and x here, right? We know that the derivative of ln x is 1 over x. So maybe some chain rule is happening here, and we just need to figure out what that is. So I'm going to do u sub. Let u be ln of x, and du will be 1 over x dx. Now when you do that, and then you replace everything with u, it actually cleans up really nicely. So let me just take care of the 1 over ln 2 here, right? And now the integral, so ln x is just u, right? And then 1 over x times dx is just du, right? So here we just have the integral of u times du, which is a very simple power rule, right? We just add a degree and then divide by the new degree, right? So that means it's u squared over 2, right? And then plus c, of course. All right, and then do reverse u sub, replace the u back with the original expression. So we get what? Ln x quantity square over 2 ln, oh, not ln x, ln 2, okay, plus c. And that's it. All right, next I just want to show you guys a few more examples, and hopefully it will give you guys a better idea on how to integrate with log and in this case a trig function. Right? So we have never talked about what the integral of cotangent is, right? We know sine and cosine, they are derivative and integral of each other. Of course, you need to consider positive or negative, right? And we have secant, secant tangent, tangent is secant square, and so on and so forth, right? So we have never actually ran into the integral of cosine. Now we know that the derivative of integral of cotangent, we know that the derivative of cotangent is negative cosecant cotangent, right? But we have never talked about what the integral of cotangent is. All right, so here we go. Now, of course, again, give this a try if you want to. You can pause the video. But first thing we're going to do is we're going to rewrite cotangent x as cosine x over sine x. Okay. Now we know that cosine is the derivative of sine, so somehow we want to take the derivative of sine to get cosine. And again, I'm going to do u sub here. I'm going to let u be sine x, then du will be cosine x dx. And this is going to be very nice because when you clean everything up, you just have 1 over u du. Okay. Again, feel free to pause the video anytime if you want to take a look at that. But cosine dx right here, that is du. And then we have sine x, which is u along in the denominator. And that is ln of u. Okay, now I'm putting u in the absolute value because we're not sure that u is positive. And reverse sub, ln of absolute value of sine x. Right? Now in this case, since we don't know what domain we're working on, we don't know if x is strictly positive or if sine of x is strictly positive, but sine of x can be negative even when x is positive. So I'm adding the absolute value there. And I forgot something very important. Do you guys know what it is? Right. Plus c. Right. So plus c will be like minus 1 if I miss it on the exam, right? Minus 1. So don't forget plus c, right? Put a note on your next to your computer screen now. Okay, so there is another 2 integral of trig that's not that common, but you know, it's sometimes useful having this on your notes. Right, so we have the integral of secant and integral of cosecant. Right, you can see that they look pretty crazy, right? And that's actually because it's actually pretty hard to go from the integral of secant or the integral of cosecant to the right hand side. Right? What I'm saying is this direction is pretty hard. It requires some sort of trick in order to evaluate this integral. If you're interested, they are actually in the textbook. It's a pretty short read, and it includes kind of like a really neat trick that you need to do in order to evaluate this integral. But for now, you can just take this for granted and use it if needed. All right, now it's your turn. Go ahead and try to evaluate this indefinite integral on your own. Pause the video, take a few minutes, and try to work it out. If not, if you don't work it out, or if you have something that you think it's working, then continue. We'll show the answer in a second. All right, so let's see. Off the top of my head, I probably would want to do u sub. Right, so u is ln x, and then du is 1 over x dx. And let's see, what do we have here? All right, that'll become ln of u over u du. Okay, and that actually looks familiar to our last example. But if not, then Let's do this. I'm going to do substitution again, but I can't use U anymore. Let's say I'm going to use V. I'm going to let V be ln U. And then dV is 1 over U du. And then our new V sub is going to look like V, just V, right? V times dV. Okay? And then that's just a simple power rule, B squared over 2 plus C. Reverse sub, V is equal to ln U, so that's ln U quantity squared over 2 plus C, and then reverse sub again, reverse place U with ln X. So what is that? That is ln of X square, the whole thing square, over 2 plus C. Okay, a pretty fun example, right? You get to do a U sub twice. Well, not U sub twice, you do U sub and then V sub, or any letter of your choice. There you go. Hopefully this is not too bad. And that will be all for 7.1. And see you guys in office hour. Take care.